to chapter 18 and see how far we can get. And this one will feel a little bit more physicsy, I think. Okay? Chapter 18. Let me change my notes so I'm looking at the right thing. And let's see where this gets us. So chapter 18 is really all about one topic. And you see it there listed in the title of the chapter, which is called the kinetic theory of gases. First of all, just having the word kinetic makes me start to think physics, right? It's like kinetic energy. Like, physics things. That's exciting. The kinetic theory of gases. And what this is going to do is allow us to make a connection, once again, between the macroscopic and the microscopic. Can I do something? Can we generate an equation that tells me things that are connected between what molecules are doing and what I can measure externally on a macroscopic scale with my instruments and senses? So you could think of this as sort of a molecular interpretation of a state variable like temperature. And if you just slide through a couple times here, you'll notice molecular interpretation of temperature. It's going to take us 2 slides because there's like a lot to talk about to try to get to this connection. It will take us almost the rest of the class period. Okay, so prepare yourself for like a long, drawn-out sort of thing. That involves a good bit of physics. So what we're going to do in the kinetic theory is we're going to use Newton's laws. So all of this is based on Newton's laws. All of it's based on Newton's laws. Here's the thing. What we would like to do is look at every individual molecule in a gas, right? It's just a piece of mass that's moving. In Physics 7a, we learned how to deal with pieces of mass that are moving and colliding with things, and we learned about how to deal with Newton's law as it relates to changing momentum, perhaps. Yes, maybe you remember some of that a little bit, all right? We could use Newton's laws, and if it were possible, look at every individual molecule and watch what it does and apply Newton's laws to that and get equations out of it. But of course, when we're talking about 10 to the 23rd level of molecules, that's going to be a little difficult. Not to mention, I can't really see them very well, okay? So what we're going to do is use Newton's laws, but we're going to use it in a way that involves statistics and averages instead of looking at each individual mass inside the gas. There's just too many particles to look at. So to do this, we are going to have to make a few different assumptions. We're going to look at a particular section of gas that's contained and try to look at its collisions and sort of add those up over all of the molecules and try to look at sort of the average collision and see if we can somehow look at the individual motions of molecules and make a connection up to the temperature of that gas. To do that, first of all, take a look at these 4 assumptions we're going to make, and this will help us sort of imagine the gas that we're looking at. So first of all, we are going to say that there's a bunch of molecules. That's pretty obvious in any gas that we're looking at. We're going to say that this number of molecules is given the symbol capital N. Each one of them has a mass little m, and we're just going to say that they're moving in a bunch of random directions. I don't really know what's happening with the gas that I've got contained. We just know that the molecules are moving in all sorts of different directions, and they have a variety of different speeds. There's no reason to think that they're all going to be moving at the same speed in a bunch of different directions. They're all just sort of moving around randomly, just like the air that's in front of me right now, right? Like if we could look at it and look at the molecules, there'd be little air molecules just sort of moving around in all sorts of different directions, all right? Number 2, we're going to say that ideally speaking, they're really far apart. If you look at the distance between any 2 molecules compared to the size of an individual molecule, from their perspective, they are crazy far apart from each other. The scale is very different between those 2 concepts. So molecules are mostly far apart and spread out. We're going to say that they only do a couple of things. They only interact when they collide, which is going to be pretty occasional, right? If they're small and they're really far spread out, that's kind of like asteroids going through the solar system, right? Like occasionally they hit planets, but it's not like it's happening continuously, all right? So they're going to collide sometimes, and when they collide, well, classical mechanics or Newton's laws will tell us something about those collisions. The only other thing that they can do is, well, the walls of the container that we've put the gas in. Sometimes, actually quite often, they're going to collide with the walls of the container in some type of collision and bounce off. It's those collisions with the walls of the container that allow us to detect a pressure. Okay, they're pushing on the walls of the container by colliding with it. And we're going to finally, at the end, say that all of these collisions are elastic, meaning we're not saying the molecules stick together or that they're sort of like damaged in some way. They just bounce right off of each other, and they're the same molecules as they were before and after any of those collisions. And finally, we're going to say that the collisions happen really, really fast, which is typical of collisions, right? If I run into the wall, my collision with the wall is a quick thing, right? It's like, yay, I'm running at the wall. You kind of want me to, don't you? A little bit. I run at the wall. I still haven't collided. Time is passing. Haven't collided. I collide, and even if I'm still on the wall or like stuck into the wall a little bit, like the collision is over. It happened. Like it didn't happen. Oh, it happened, right? The collision is a very, very brief period of time. That's what we're going to say is happening here. Molecules are flying around. Maybe it takes them a long period of time to go from one side of the container to the other. But when they collide with each other or with the wall, it's like, that's done. It happens in almost an instant. It's very, very fast. Okay? Do you have any questions about the 4 assumptions going into this? You're like, I don't know enough about where we're going yet to ask a question about the assumptions. Okay? So keep them in the back of your mind. And if something comes up related back to them, let me know. So let's see here. Where are we going to start with this? First of all, we are going to add to this that pressure as a whole, as I said just a moment ago, we should write it down just to make sure we have it in front of us, comes from collisions with the walls. And we can say that Boyle's law seems to agree with this assessment. Boyle's law seems to agree. Remember, Boyle's law, if we go back to our previous slides, it's the one with the graph that's in the top right. Where is it hiding? There we go. Boyle's law, right? The pressure goes up as I decrease the volume, and they're inversely proportional to each other. So that means if I cut the volume of my container in half, well, I have the same amount of gas in there. I should sort of double the amount of collisions by cutting the volume in half, which means I'm going to get double the amount of pressure. Well, that seems to agree with this idea that, well, I've got little molecules that are flying around hitting the sides. If I just cram them into a smaller space, of course they're going to hit the sides more often and increase the pressure. All right? So Boyle's law seems to agree with this idea. Here's the way we're going to start. We're going to use this volume over here on the right. We're going to use a cubic container just to make life easy for ourselves. Okay? So let's pretend that we have a cubic container of gas. Whoops. And we're going to say that the walls have length L and sides have area A, as you can see in the diagram. Walls are all of length L and the sides have area A. And let's focus on, first of all, collisions with the left wall. Okay? And if you're thinking like, we're going to do one wall at a time and look at the collisions with it and somehow calculate pressure from that, well, if all of the walls have the exact same area and everything's kind of moving around randomly, if we look at the collisions with one wall, really it's going to be the same everywhere, so we're not actually going to have to deal with all 6 walls. We just need to look at this once to sort of build up the conditions and what's happening. Okay? And you can see in this diagram, if I were to zoom in on this, notice they even sort of, maybe you could imagine, I don't know, maybe this one sort of just bounced off that wall. Maybe it went in like this and bounced off that left wall. Okay? So we're only looking at collisions with the left wall of the container. So here's what we can say about those collisions. According to Newton's third law, And it says that the force of molecule on the wall equals the force of the wall on the molecule. By the way, Newton's third law, N3L. I kind of like that. I'm curious who's figured out why I might like that. Think a little bit. Yeah, it's like my initials, right? With a 3 in the middle. It's like all of Newton's laws are like N1L, N2L, N3L. I kind of want to change my middle name and just have a number. I get to pick my favorite Newton's law. Just put that in there. That'd be kind of cool. Yeah, I could be N2L. That'd be fantastic. Yeah, I'm not going to do that, though. All right? So, Newton's third law says the force of the molecule on the wall equals the force of the wall on the molecule. So, we can say that this force is equal to the rate of change of momentum. This force is equal to the rate of change of momentum. And if we're looking at the left wall, we're only going to have a change in momentum in one direction. Again, think a little bit about that molecule sort of going up and to the left and then bouncing off and going up and to the right. Because of the nature of the force, which points straight to the right, its momentum only changes horizontally. That force can't impact its momentum up and down in the y direction or out towards you in the z direction because of the nature of that force from the wall. So we're going to only have a change in momentum in the x direction. Only going to have a change in momentum in the x direction. So we could write perhaps something like this. We could say that the initial momentum of that molecule, if it's bouncing off the left wall, it means it has a negative velocity. So we could write that as minus m times velocity in the x direction. And when it bounces off, if it's an elastic collision, it's going to have the same velocity in the x direction coming out. So we could say that the final momentum is positive m times vx. So if I put those two things together and look at how much the momentum has changed, remember that's going to be p final minus p initial. So I'm going to end up with two negative signs there, which means that the overall change in momentum is going to be 2 times the mass times the velocity in the x direction. Ugh. Let me pause for a second, let you absorb what we've got so far, and see if you've got a question. Because we filled that slide. We might need 3 slides, actually. I'm not sure. It's a long and involved thing. How are we doing? Questions over here? Anybody? Anything? No? You're okay? Are you alive? Still alive? Okay, that's good. Oh, yeah? Oh, yeah, you're still alive. Well, that's excited and alive, apparently. I don't know what's happening there. All right, so we've looked at how much the momentum has changed. If you look back at our force equation, essentially we've found something about the numerator of that. But we really haven't talked about how much time it takes for the collision to happen, okay? So the next thing we need to do is address that. So let's go over to the next slide where we've got some space and talk about how much time occurs in between the collisions, okay? If we're looking at the average force, and this force is coming from collisions of the molecules with that left wall, the average force on that left wall, well, the time of the collision itself is almost nothing. What's really going to matter if I'm looking at average force is how much time it takes before another collision happens, okay? In other words, we're looking for average force like it pushed on the wall a little bit, and then sometime later, another one comes along and pushes on the wall. How much time does it take for the collision to happen and then to wait for another collision to happen? Okay, so when we're looking at that denominator, we're trying to find something about how much time it takes in between collisions. So let's write that down. We could say that delta t is equal to the time between collisions. And again, the time of the collision is essentially negligible. We're not going to worry about that part at all. So maybe let's just watch one molecule Okay, you can imagine like that molecule on the left side, it bounced and now it's traveling up and to the right. And maybe it does something like hits the right wall and then eventually bounces off a couple of other walls and makes its way back to the left wall. Okay, we don't know exactly what its path is going to be. But we do know something about this. We do know that it has a velocity in the x direction, and it goes this way with that velocity, and even when it collides with other walls, that velocity is not going to change. Okay, so it's going to finally make its way back at that exact same velocity. Okay, the velocity in the x direction is going to be a constant. So here's what we can write, and I can't get this to work. There we go. Okay, we could say that the velocity in the x direction is going to be how far it has to travel in the x direction over how much time it takes. So just assuming a constant value, we can use that equation for the velocity. And if we want to look at how long it's going to take to go all the way over and all the way back, well, I know that that's going to be 2 times L, the length or the width of our little box, of our container. And in the denominator, we have delta t still. So that means I can rewrite this as delta t is going to be equal to 2L over Vx. This is the amount of time for another collision to happen with the left wall by that molecule. Are we still doing okay? That one maybe felt like, if you're hanging on to it at least halfway, you're doing pretty good. Okay, question?
So are we just assuming that the particles don't collide with each other outside of the wall?
We'll deal with that in just a little bit. Okay, we will come back around to that. Anyone else? I'm coming back down because, again, it's terribly hot up there. You people are struggling, aren't you? You're like, no, I like the heat. The heat is fantastic. It helps me expand. It's great. I love it. I don't know why you'd like that. All right, so let's see. We're going to take these two equations now and put them back together in this force equation. I have a numerator and I have a denominator, so I can write an equation for the force at this point. So we could say that the force is dp dt, or we could rewrite that as delta p over delta t. And let's plug in these two equations we have for the change in momentum and the change in time. So let's see, what was delta p? That was 2 times mvx, and delta t is 2L over vx. And let's rearrange that. So the 2's are going to cancel out, and we're going to end up with mvx squared over L. And this is the force, well, from that one molecule on average on the left wall, okay? So let's add a couple of notes to this. We can say that, first of all, just to help us remember this, collisions with the top or the bottom won't change Vx. Collisions with the top or bottom won't change Vx. It'll just keep having that constant value. Again, collisions with the top or bottom are going to apply a force up or down. That's not going to have any impact on what's happening horizontally, okay? So it won't impact our Vx. This is why we could say that's a constant. And also, we could say that collisions with other molecules we'll say will change the momentum, but we'll say we will include all molecules. So in other words, we're going to add that in to our sum overall. So whatever happened with collisions with other molecules, change the momentum, but we're going to do a sum so that we're not dealing with just one of the molecules. We're going to deal with all of the molecules that are hitting the left wall. And when we do that, that includes anything that gave or took momentum from our individual molecule when dealing with other molecules. So number 3, and I think I was numbering these, right? Yeah, number 3. How do we find the force from all molecules? Again, on the left wall. Now keep in mind, if I have a bunch of random motion, there's no reason to think that I'm going to have periods of time where it's like there's a bunch of strikes against the wall. and then periods of time where maybe nothing hits that wall at all. So there's no reason to think that maybe the rate of collisions is increasing and decreasing because the motion is completely random, which means this force from all the molecules on the left wall should be roughly constant. It shouldn't be something that's changing. So to include all of that, here's what we want to do. Let's use our force equation from above, the one that we just found. So F is equal to mvx squared over L. L is a constant because it's about the container. M is the same value for every single molecule. And Vx, we don't know that it's the same for every molecule. We know there's a bunch of different velocities, as we said in one of the assumptions. So that's the only thing in there that's different. If I want to find the total force, or rather the total force, we'll say on average, since we're looking at averages here, I need to add up all of the individual forces where the only thing that's different between them is that Vx. So we could change this over and say that the force total average, or excuse me, let's just say this is force total at this point, is equal to m over L times Vx1 squared plus Vx2 squared plus Vx3 squared. Buckle in, we need to go to 10 to the 23rd. So plus Vx4 squared plus, yeah, you get the idea. We're not going to keep going, all right? We need to add up all of the individual forces from all of those molecules. And let's see how we could switch that over to an average value. Let me go to a little aside here. We could say that Vx squared average would simply be adding up all of the individual velocities and then dividing by how many I added up, just the way we calculate any average at all. So we could say that that's going to be, Vx1 squared plus Vx2 squared plus Vx3 squared plus however many of those we have divided by the total number of molecules. Okay, it's the sum of all of those individual velocities squared divided by the number that I added together. And I've got one of them for every molecule that's in the gas. And that notation on the left, Vx squared, and then an AVG at the bottom, that's kind of extra and useless. Let's rewrite that a little bit cleaner. We could write that as Vx squared and put a bar over the whole thing to denote the average. Which means I can make a little substitution here, okay? Notice that this part of the equation is what we have just above. So I'm going to get rid of that sum and just plug in n times Vx squared average. Okay, we're going to use that equation to make a substitution. So now we can write force, the force total, and now this is going to be an average total value, is going to be m over L times capital N, the total number of molecules, times Vx squared average. And at that point, we're going to take a deep breath, because that fills up slide number 2, and there's a lot of stuff that's happened. There's a point to all this, I promise you, okay? The payoff, at least in my opinion, is worth it at the end. So just bear with me a little longer. We'll get there, okay? Does anybody have any questions about this particular slide? Notice where we are. We've now included all of the molecules, and we have an equation for sort of this average constant force that's pushing on the left wall because of all of those individual collisions, okay? There is this constant force because there's thousands and thousands and thousands and thousands of collisions happening every instant, okay? So what are we going to do with that? Well, first of all, I need a new slide because I am completely out of space here. So let's see, add a page below. That should work. And I think it's going to come out in a different aspect ratio, but that's okay. We'll figure it out. All right? So number 4 on our list of things here is perhaps we should ask, what about all the other directions? Notice, all we've been doing is the x direction. In fact, our force equation is specifically about the velocity in the x direction, when we know that these molecules are moving in the y and z direction as well. So we have to do something about that so that we actually get the total force. So we could say, first of all, the square of the total velocity is going to be the x velocity squared plus the y velocity squared plus the z velocity squared. Harkening back to Physics 7a just a little bit. And if we were to write this exact same equation using averages, we could say the same thing about the relationship between the averages of these. So I could say that v squared average is equal to vx squared average plus vy squared average plus vz squared average. But keep in mind, remember again, the motion is random. There is absolutely no reason to believe with random motion that any of those three velocities in the x, the y, or z direction is larger than any of the others. If it's truly random motion, really they should have the same average velocity in any given direction, which means I can simplify this just a little bit. So let's put some dots there and say that all directions should be the same. Which means that vx squared average equals vy squared average equals vz squared average. Which means I can rewrite this v squared average as just 3vx squared average. They're all the same. So if I add all of them up, I can just express it as one of them, which is the one we've already been using the whole time. Are you okay with that little jump? Okay? None of them has preference, and I've got motion in all three directions. So let's take this, and we could say that vx squared average is equal to v squared average over 3. And we're going to plug that back into our force equation. Plug that back into our force equation. So our force equation looked like this. We said that F was equal to what? I got lost. M over L times N Vx squared average. Yeah? Is that what we had on the previous slide? Yes. Good. So now if we plug this in, it changes it just a little bit. Now we've got M over L times N V squared average over 3. And now we have an equation that's not just dealing with the x direction, it is dealing with all three directions. Okay, so this is the actual total force that's happening on that left wall, dealing with all the motion of the molecules. Okay? So now that we have force, everything that we've been talking about with state variables, that's pressure, volume, and temperature. Force isn't one of those. Like, how do I measure the force on the wall? That's a little hard to do. Instead, since I have a force that's spread out over an area, pressure is a better way to denote that. So let's rewrite this equation in terms of pressure. So let's change this over to pressure. We know that pressure is equal to force over area. So let's plug in our force equation, which is M over L N V squared average over 3. And the area in the denominator, we're just going to leave that where it is at the moment. And let me rearrange this, pulling this L down into the denominator as well. So now I've got M N V squared average over 3. Actually, let's move that 3 up front as well and write this as 1/3. And now in the denominator, I have L times A. What's L times A? It sounds a whole lot like volume, right? So this is 1/3 Mn V squared average over the volume. Uh-oh. Actually, not uh-oh. Do you see what's coming just a little bit, maybe? Something familiar from the end of last chapter. Yes, perhaps. Notice we've got a P and we've got a V. Ooh, that should look a little familiar. So let's write a number 6. So we're going to rearrange this and take a look at what's happening. Rearrange. So now I've got P times V. The left-hand side of the ideal gas law somehow came out of this mess. right? It seems a little bit like a miracle at this point. Like we made some assumptions. We did some Newton's law stuff, like just looking at one wall, did some averages, and now all of a sudden I've got PV, which is something that we already had, okay? So PV is equal to 1/3 MNV squared average. Let's compare that to the ideal gas law itself here in just a second. I'd actually like to rearrange this a little bit. You might not like this, but you'll see why it's true in a second. I'm going to rewrite this as 2/3 N times 1/2 MV squared average. Multiply that back through and you'll see that it's exactly the same as what we had before. I basically wanted to get a half. So the way to do that was like factoring out at 2/3, okay? Because now I have 1/2 MV squared, which we know is kinetic energy from last semester, right? So this is average kinetic energy, which means that we can now write this as PV equals 2/3 NK average. It's sort of another version of the ideal gas law, but now we're not dealing with temperature anymore. On the right-hand side, we're dealing with kinetic energy. Where's that kinetic energy coming from? It's coming from all those molecules moving around, right? All that motion that's happening microscopically gives me an average kinetic energy that's inside that gas. And we know just based on the fact that the right-hand side of that typically has temperature in it, that must be associated with temperature somehow, okay? So let's compare to the ideal gas law as we know it from before. So let's just write that down. We could say that PV, and I'm going to use it in terms of molecules, so that's N times K sub B times the temperature. Since we've been dealing with individual molecules, we might as well use that particular form, which means that these two things are equal to each other, right? So now we have, let's see, N K sub B times T equals 2/3 NK average. The N's cancel out, and we're left with what? We've just got K sub B, the Boltzmann constant, times the temperature is equal to 2/3 times the average kinetic energy. And let's go ahead and just solve that for kinetic energy. So kinetic energy on average is 3/2 Boltzmann constant times temperature. And it's done. What did we do? You're like, I don't know. You've been talking for forever. Could you please shut up now? I get that, all right? There was a lot of stuff. Let me scroll back 2 slides. We said at the beginning that using Newton's laws, stuff that we know how to deal with, we were going to take all of these molecules in the gas and somehow make a connection with this idea that they're all sort of moving around in there randomly, and make a connection between that microscopic world up to something that's macroscopic, something that I can just look at the overall gas and measure it. If we can make that connection and then experimentally verify it, well then I've sort of from a macroscopic level proven that there are little molecules that are down there moving around, all right? And we did all that and derived a really simple equation that connects the microscopic world, right? That side is about individual molecules that have motion. They have kinetic energy. There's a total average kinetic energy of all those molecules inside, and we've connected that to the temperature, which is a macroscopic state variable. Kinetic energy is connected to temperature. And I think that this agrees with the way we think of it, right? If I heat it up, if I make a gas hotter, it makes sense that like all of the gas molecules should be moving around more and faster, right? It agrees with sort of our intuition about the way we think gases should work. The kinetic energy, on average, is directly proportional to the overall temperature of the gas, okay? There are 5 minutes left, which means we should cover lots more things, right? No, I kind of knew we would get to the end of that and be like, whoo, whatever time it is, that's about enough, all right? We're going to delve into that equation a little more next time, but we survived the derivation. Congratulations. I will see you on Tuesday. Goodbye. We could draw one big conclusion from this, which I didn't quite have time to write down. Just in general, higher temperature means the molecules are moving faster. And I think that's both what we would expect the result to be. That's sort of our intuition. We imagine things in there are moving about more as the temperature gets higher. And also, it fits exactly what our assumptions were at the start. It all sort of comes together. What we didn't have time to do is to take this apart a little bit and start to talk about, well, not what the kinetic energy of these molecules are, but actually what their velocity is, to go from kinetic energy down to velocity. So a couple of things here at the bottom of this slide, and then we've got a whole slide on it coming up. First of all, let me rewrite this. 3/2 Boltzmann constant times T. That is equal to kinetic energy, so that's equal to 1/2 mass times velocity squared average. And let's solve that for the velocity, okay? So let's see, we've got a couple of halves here that are going to cancel out, and then I've got 3 kBt over m equals the square root of this thing. So the square root of the velocity squared average, of the average velocity squared. Which is something a little bit special, right? If I look at the things, the mathematical operations that are happening here, we've got a root, and we've got a mean, and we've got a square. So you might have heard of the term root mean square in different quantities before. That's exactly what this is. This is the root mean square velocity, which isn't actually the average. It's just the quantity that sort of happens to come out of this equation when we're attempting to solve for velocity. So keep in mind, this is not the same thing as V mean, the average velocity. It turns out that there's about an 8% difference between the two. So this VRMS is just sort of what happens to come out when I attempt to solve for velocity in this particular equation. Yes. What's happening? Oh, yeah, did I not take the square root of both sides? My apologies. Thank you. Details. So taking the square root of both sides gives us VRMS. So how does this relate exactly or more specifically to the average velocity, to the mean velocity? Let's take a look at everything that's happening here. And there's a lot that's going on this slide, first of all. Remember the gas. We've got a gas that's contained in some way, and we're imagining molecules that are all moving about the gas in random directions with a bunch of different velocities, okay? We can start to sort of figure out what those velocities are. Well, first of all, with what we did here on the previous slide, we start to get some feel for maybe on average what the velocity of the molecules are. But they're not all traveling at the average. Some are going to be faster, some are going to be slower. And it turns out if we were to plot all of the different velocities of the molecules, we would get a graph that looks something like what you see on the left, where you can see there is a grouping of stuff around the average, and then there's some that are going much, much slower and some that are going much, much faster. This is known as the Maxwell distribution of speeds, and a little bit more specifically, this is the most probable distribution of the speeds of the molecules in a gas in random motion. The most probable or the most likely distribution of the speeds of the molecules in a gas that are all moving about with random motion. So in other words, a graph of the number of molecules versus velocity means that if we were to say look at a little tiny section of this graph that maybe represents a small range of velocities that we would call dV, then this little area under the curve here is simply the number of molecules. In other words, that represents the number of molecules that are traveling with velocities in that little range that we've specified. So you'll notice they have pointed out 3 different velocities on that graph. Is it safe for me to zoom in? Or are you still writing the words at the top? They're just going to start going away slowly. Write faster. I don't know why this won't smoothly scroll the way I'd like it to. There we go. Now it's just getting frightening. What are we going to find inside here? Be kind of fantastic if I keep zooming in enough and then, but I didn't prepare in advance, so I have to do that later. All right, so you'll notice 3 different velocities that are pointed out. First of all, we've got VRMS from the previous slide. You'll notice it's not at the peak of the graph. It's not the most likely. It's also not the average. It's a helpful quantity, but it's a little bit off from these other 2. Again, it's just sort of what comes out of the calculation that we had previously. You'll notice just a little bit lower in velocity, we have the average or the mean velocity. The average or the mean velocity. And we're going to look at how to calculate some of these here in just a second. And then finally, VP, which sits at the peak of the graph. And again, this is a probability curve. It's a distribution of likelihood that a certain molecule will have a certain velocity, which means the peak of this will be the most probable velocity. There are the most molecules that have that particular velocity. So if you were to pull one out of a hat, well, it's most likely to be that one, but, well, there's a lot of molecules that have a lot of different other velocities as well. It's the most probable velocity. How are we doing so far? You're good? Everything making sense? Go Tigers. What's the Clemson connection? Family. So you don't know anything about me, do you? I got my PhD from Clemson. So now I have to memorize your face and give you an A. Because fantastic. No, clearly I can't do that, but go Tigers. And lest you think I'm not serious, oh, look, hiding right here on my bag, the Clemson Tiger paw. So I'm representing as well. All right. I feel like we should start a cheer or something because we probably know a few of the same ones. National champions, for those of you who don't know, in football. Good times. Anyway, that's off topic. I'm distracted now. Let's see. So what does this curve look like mathematically? Bear with me just a second. So if we wanted to look at the mathematical equation of this distribution curve, it's represented by a function of velocities, and it looks something like this, and this is going to go on for a while. 4 pi times the number of molecules that are in the gas times m over 2 pi kt, and that's the Boltzmann constant. All of that to the 3/2 power. I'm not done yet. There's more. Let's see, that is times v squared times e to the minus 1/2. Don't you start to feel like I'm just making up symbols at this point and just putting them at random places in the equation? It kind of feels that way. Minus 1/2 mv squared over kt. I could keep going and actually start making up stuff at this point, but alas, that's what that function looks like. Ugh, a bit of a mess, yeah. And lest you think we are making stuff up, it turns out this has been experimentally verified. Someone had the painstaking job of just like reaching into a gas and being like, how fast are you going? And then plotting it, and then reaching in, how fast are you going? And it took a long time because there's a lot of molecules in there. So it has been experimentally verified. And by the way, the thing on the previous slide, this average kinetic energy is equal to 3/2 kBT. That's been experimentally verified as well. So all of this is not just theoretical. Okay? All of this has been experimentally verified. So let's see, what else to add to this? If the area under the curve in a little range like that is the number of molecules that are going at that particular velocity, one thing that must be true is that if I integrate this from 0 to infinity, what should I get? In other words, if we find this whole area under the curve, what's that going to give me? I hear N out there. Which N? How about big N, the number of molecules in the gas? Because there's a plot there on the point for every molecule in the gas representing its particular velocity. And then finally, this particular curve depends only on temperature for a given gas. Take a look at this graph here at the top. So where this curve is located exactly depends only on temperature once I've chosen a gas. So we have a gas, we change its temperature, it's going to change the shape of the curve a little bit. You will notice that it shifts right with higher temperature. And you can see two curves there on the top. We've got the one that peaks at a little bit lower temperatures at 273 Kelvin. And then if we go to 310 Kelvin, that curve is peaking a little bit farther to the right. Which makes sense, right? Higher temperatures should represent higher velocities of molecules on average, which means I've got more of the molecules at a higher velocity. So that seems to fit what we would expect. And by the way, I just noticed this is not tracking terribly well today, is it? So I think what I'm going to do, I'm going to disconnect real quick and see if we can make it better. Let's try it again. Come back. Let's see if it's any better now. Oh, it's all still janky. What are we going to do? All right. Alas, just assume I'm writing smoothly and wait for stuff to appear. It'll be fine. So a couple of different things we can do. First of all, let's see if we can find this mean or average velocity. Finding the mean or average velocity. So the way we're going to do that is something like this. The mean velocity is going to be equal to the integral from 0 to infinity v FV dV over n. So I'll write it down. Let's talk about it, make sure we're all on the same page as far as why that makes sense. If I want to find the average, I simply need to add up all of the individual velocities and then divide by how many velocities I've added, right? So if you look at that equation, essentially this is going to tell me the number of molecules, and we're multiplying each one of them by their individual velocity. So we're going to have a sum of all the velocities of the molecules, and then we need to divide by how many of those were in the sum, which is the total number of molecules. So this is going to give me an average. Really, this equation is no different than any other way you'd calculate an average, okay? It just looks a little more funky, all right? I'm going to let you do that integral. We're not going to work through that. Actually, you don't have to do it either unless you really want to have fun. So you could plug in the Maxwell distribution into that. It may not be as hard as we think. There's a lot of constants in there. There's some velocities hiding in awkward places, perhaps, so that could be a little fun. I'm going to tell you how it works out. It turns out that it's just 1.6 times the square root of kT over m. Don't you wish it had just been 1.6? What a way to end that would be. It's just like the average. It's just 1.6. All that work for nothing. The mean or average velocity will work out to be 1.6 times the square root of kT over m. How would we find Vp, the most probable velocity? For the most probable velocity, we need to find the peak of that graph. So to do that, we need to take the first derivative of that curve with respect to velocity and set it equal to 0. And then solve that for the velocity. So we're finding where the slope of the graph is equal to 0. And if you work that out, you will find that Vp is equal to 1.41 times the square root of kT over m. And clearly I needed 2 slides for this because things have just gotten a little crunched. So let's see. Let me box a couple of these equations. Here's the average velocity. And then here is the most probable velocity. And on the previous slide, we have an equation for the RMS velocity. So at this point, we know quite a bit about the different velocities that are occurring of the molecules in the gas. Yes? It's K sub B. Yeah, I just didn't want to put that in there. It's a little messy, adding too many subscripts. K times T. K is the Boltzmann constant. Anything else up there that's bothering you or seems incorrect? Yeah. I'm sorry?
How do you experimentally determine the distribution?
That is an excellent question. I was not involved in those experiments, and I have not read about them, so I don't know off the top of my head. I'll have to let you Google. I do not know. Like I said, I think you just pulled them out of the box, right? And asked them. I don't think it's going to work. Anybody else? Okay. So we know a good bit about how temperature relates to the velocities of the molecules in the gas, all right? Everything that we did there, however, was about ideal gases. Ideal gases, remember, are the case where it follows PV equals nRT. It follows all of that stuff that we talked about. And also, it only applies when we're at a temperature that's far away from liquefaction and we're not dealing with a gas that's terribly dense. So what happens if all of a sudden I relax those conditions a little bit and maybe we start to lower the temperature a little bit more, or maybe we start to apply a little bit more pressure and put the gas a little closer together? Well, all of a sudden we're going to have behavior that no longer follows the ideal gas law, and we might call these real gases. So if you take a look at this graph on the top right, and I really hate that that's not tracking fast because it makes it difficult to talk about. First of all, keep in mind we've got 4 different curves here, starting with D and going up to A. That is higher and higher temperature, so we should draw that in to begin with. As you go this direction, those curves represent higher temperatures. And also this plot of pressure versus volume will allow us to at least qualitatively begin to understand the behavior of real gases. If I remember correctly, we look at these a little bit more in the following chapters, but we can start to kind of understand what's happening. So let me add here as well, since I said it but didn't write it down, real gases, this is near liquefaction or at higher pressure, which would mean higher density. Near liquefaction or at higher pressure, which would give us higher density. So on this particular graph, the dashed lines are what is predicted by the ideal gas law. And the solid lines are, we'll say, actual behavior, actual or real. Solid lines indicate what actually happens. I'm just playing again. I have to entertain myself while you're writing, right? So what's one to do? Dashed lines are predicted by the ideal gas law. Solid lines are what actually happens or what's real. So notice if I go over here, all these parts of the curves are at low pressure. And really at this point, no matter what the temperature is, you can see there's no difference between a dashed and a solid line. They're overlaid here, so we don't see the dashed line at all. So the real behavior exactly matches the ideal gas law. It's only as these curves begin to go up, right? We're getting higher pressures down here that we see some of them begin to diverge. We get a curve that's a little bit different, okay? So you can see this divergence between the two, and we don't get just like a curve that just simply goes up as we saw in the previous chapter, all right? So what exactly is going on here? First of all, why is this happening? Why the deviation? And we're going to say according to kinetic theory. Why the deviation according to kinetic theory? Remember back to the assumptions on the first slide of this chapter. We listed 4 different assumptions, and we talked about how the molecules of the gas were going to be interacting. We essentially said that occasionally molecules would hit each other in an elastic collision and just bounce off. They would interact sometimes like that, but all of the energy transfer would be perfect, essentially, in the elastic collision. And they're also going to hit the walls and collide with the walls elastically as well, which just changed their direction. We assumed that nothing else was happening in the gas. We assumed that there were no other interactions that would cause a problem. Well, it turns out, you can imagine that if I lower the temperature, all of a sudden, things aren't moving around as much. They're going to spend a little bit more time near each other, first of all. And second of all, if I increase the pressure, I'm pushing them closer and closer together. What happens then is we start to get interactions in other ways that we didn't account for in our first derivation. In other words, now we start to have other attractive forces between molecules coming into play. And again, this is all happening because we're going to lower temperature and higher pressures. Lower temperature and higher pressures. These attractive forces mean that the molecules are pulled together into a smaller than expected volume. These molecules are pulled together into a smaller than expected volume. And you can see on those top two curves, that's exactly what the deviation is every time. So as I go from dashed to solid line, it's to the left and below, to a lower volume than what the ideal gas law predicted. Which sort of makes sense, right? If I have extra attractive forces that are there, instead of being what I expected it to be, they're all going to pull themselves together just a little bit more than we would have expected if we ignored those contributions. Are you okay with that relatively rough description? Okay? Explaining the difference between the two. So let me point out a couple of different things on this particular graph, and I like to keep writing with the pointer. That doesn't work at all. First of all, let's take a look at curve D. Curve D, the one on the bottom, the one at the lowest temperature. You can see that they've drawn this as passing through a liquid vapor region, which means that as we go from point B on the graph over to point A, we have liquefaction. Curve D represents liquefaction. And then notice after liquefaction, as you go farther to the left over at point A, look at how steep that curve gets at that point. Keep in mind at that point it is a liquid, which we should add here. And it makes sense that as I go to higher and higher pressure, because it's a liquid and not a gas now, I'm not going to be able to change the volume a whole lot. There's not a lot of compressibility once it turns into a liquid. So we get something steep where we're increasing the pressure a lot, but the volume is only changing a little. Okay? And that gets more steep as you become a liquid. Another thing that we should point out is curve C. Curve C, and especially point C on curve C. This one is at the critical temperature. This particular curve is at the critical temperature. You can see at point C, it sort of just brushes by the liquid vapor region. At this critical temperature, we can say that at temperatures lower than the critical temperature, we can have liquefaction with enough pressure. And at temperatures higher than the critical temperature, no liquid at any pressure. It's just not possible to convert that gas over. Just a qualitative description of real gases so far. Okay, we got one more slide that'll give us a little bit more information. But does anybody have any question about the PV diagram? And by the way, they didn't actually plot all of the dotted lines that they could have. I think it would have just gotten too messy. Curve C and D, they just diverge from ideal behavior kind of totally. So they didn't put that in there. You might imagine that like these actually sort of do like this as well. Yeah. But alas, the temperature is just too low and becomes a liquid anyway. So of course it's not going to obey ideal gas law behavior. Which brings us to the last slide that I want to cover in chapter 18. And I'll explain a little bit more about that statement in just a little bit. Just a little more about real gases and phase changes. We can also look at a pressure temperature graph or a phase diagram, which shows us a little bit more information. And I don't want to talk about this terribly much. Just note a couple of different things. We can look at this point, if you can see that, and this point, both of which lie at 1 atmosphere. And notice it represents phase changes for water at the temperatures we would expect. So at 0, we have a switch from solid to liquid, and at 100, we have a switch from liquid to gas. But of course, you could have pressures that are below that and pressures that are above that, and those phase transitions are going to happen at different temperatures, but you can see all of that on the particular graph. I don't think there's anything else I want to say about that you probably haven't heard in a chemistry class at some point anyway, okay? Is trying to make connections back to the idea of kinetic theory. The idea that we have all of these molecules or atoms that are in a substance, and they're sort of just flying around in there in random directions with a variety of speeds according to the Maxwell distribution, okay? So you can see here we have a list of 4 quick topics that I'm sure all of you are familiar with, but we're going to try to give them a little bit more explanation starting from the standpoint of kinetic theory, okay? So they sort of build one right into the other, and once we get to the bottom, I'm just going to basically be throwing some definitions at you so we can move on, all right? None of these topics, I think, is terribly, terribly confusing in the big picture of what we're doing in this class. So let me point out here at the top, just to make sure that you have a record of it, this is from the standpoint of kinetic theory. And I realized a little too late that there's a lot of writing on this slide, and I could have simplified it a little bit by including some of it in advance. So my apologies. There's a good bit to add in here that's just text, okay? So we're going to start with the idea of evaporation. I'll talk a little bit, and then I'm going to put the notes that are up there that goes with it. Evaporation. If you think about evaporation, which is just simply like we end up with some liquid that sort of spontaneously turns into a gas. And if we think about that from the standpoint of kinetic theory, you've got a bunch of molecules that are in the liquid that are, again, moving around at a variety of different velocities. Some of them are going to have higher velocities and hence higher kinetic energies, okay? The ones with enough kinetic energy and relatively near the surface can leave the liquid state and sort of find themselves separated from the liquid state, hanging out in the gas state nearby, okay? So let's start by writing down that those molecules with high enough kinetic energy can, we'll say, escape to the gas state. And of course, some do. Not all, a few, depending on temperatures, etc. So just thinking about what we've learned about kinetic theory, the idea that there's more kinetic energy, there's higher velocities overall. Remember that curve for the Maxwell distribution shifts to the right as we go to higher temperatures. It makes sense that with higher temperatures, we should see more evaporation because there'll be more molecules with a high enough kinetic energy. And that's exactly what we observe. If the liquid is at a higher temperature, you're going to get more evaporation than you would at a lower temperature. So it matches kinetic theory. So there is more evaporation because, let's say, more higher kinetic energy. So there's more molecules with higher kinetic energy. Yeah, I know that didn't make sense up front, but I stated it that way for a reason. More evaporation because more higher kinetic energy at higher temperatures. More evaporation because you have more molecules at higher kinetic energy as you have a higher temperature. But think about what happens. I'm losing some molecules out of my liquid. And I'm losing very specific ones. I'm losing the ones that are the most energetic. So if you think about what's happening here, all of a sudden the average kinetic energy of my liquid drops a little bit every time I lose one molecule to evaporation, which results in this being a cooling process. The reason for that is because I'm losing molecules with the highest kinetic energy. Okay? Evaporation from the standpoint of kinetic theory. Any questions so far? I think that one is probably the most logical of these. It's just like, oh, okay, that makes sense. Everything sort of fits. All right. Let me draw a nice separating line here just so that we don't mix things up. And talk a little bit about vapor pressure. Vapor pressure. And we're going to start the description of vapor pressure back with evaporation. So again, random motion, high kinetic energy molecules leave, but they're moving a bunch of different directions, which means some of those high kinetic energy molecules just happen to come right back and re-enter the liquid, all right? So just based on random motion, we're going to get some that are leaving, some that are re-entering. As more and more evaporate, then there's more and more that could re-enter the liquid, okay? At some point, that's sort of going to reach an equilibrium between the number that are leaving and the number that are re-entering, and you end up with sort of a steady state situation with the gas that's near the surface of the liquid. This pressure, the pressure of the vapor or the gas near the liquid, when sort of saturation is reached or an equilibrium is reached, is known as the vapor pressure. So how to write all of that out? We could say that this is the pressure of the vapor at the point of equilibrium. In other words, equal numbers exiting and re-entering the liquid at the point of equilibrium. Vapor pressure is the pressure of the vapor at the point of equilibrium where you have equal numbers entering and exiting. Sometimes you'll see another word in front of this. It might be written as saturated vapor pressure. Same thing, we'll just say vapor pressure, but you could have the word saturated there to sort of help you remember that the vapor is saturated at that point. No more is going to go in because there's equal numbers that are coming back out into the liquid. Okay? That is our discussion of vapor pressure. Exciting, right? We should make a deal up front. I don't think we've made this deal yet. Are you ready to make a deal with me? Okay, it's going to help. No? I heard a few people just be like, no. You're like, just talk about the slides. Don't talk about anything else. Here's the thing. I need feedback from you. Ideally, positive feedback so that we all kind of like feed off each other and create more energy. So if I say something like, isn't that great? Even if you don't think it's great, you can just lie. I don't care. Just be like, yeah, that's fantastic. And then like I'll be like, oh, they actually like it. Even if I know you're lying, like just that positive energy back, I'm like, oh, that's good. Like they're lying to you. No, but it's good. Did you hear them? And then I feel a little better. You feel a little better. And then before we get to the end of the lecture, like everybody is just rabid with excitement. Okay? So feel free to lie about your level of interest. Sound good? That's a pretty good deal, right? I think so. So, vapor pressure, that's pretty awesome, right? Yeah, I thought so. That was a little too much. Just take it down a notch, all right? Which brings us to boiling. We all know what boiling is when we have the transition from a liquid to a gaseous state of a fluid. We could say that this happens at the temperature when the vapor pressure equals the external pressure. When the vapor pressure equals the external pressure. I should put one more note on vapor pressure up there. Just don't forget this is dependent on temperature. Again, because there's more molecules with more higher kinetic energy as you get to higher temperature. Boiling happens at a temperature when the vapor pressure equals the external pressure. So think about what happens if you are, say, at high altitude. You're like, well, what does that have to do with anything? Well, we could say a few different things about being at high altitude here on Earth. First of all, we could say that we have a lower external pressure. A lower external pressure means you're going to end up with a lower boiling temperature. Which means if you're cooking something, and it's like, oh, you need to boil this rice or whatever it may happen to be, right? And you're like, it's boiling, fantastic, I'm cooking it, like everything's going to be great. Just keep in mind that boiling temperature isn't as hot as you think it is, which means that you're going to end up with longer cook times than expected. Now, see, that's kind of nice. That's a little practical advice, right? It's about food, and we all love food. Oh, fantastic, food. I don't want to end up with uncooked things. You have to cook things a little bit longer because of this lower boiling temperature, which means we can flip this around and use it to our advantage. And what if we used a pressure cooker here at maybe normal altitude, closer to sea level? A pressure cooker. Anybody use one of those Instapots? More excitement. A few of you out there. They seem to be always on sale on Amazon. It's like they really want you to buy an Instapot, which is really just an old-fashioned pressure cooker that's sort of been, like, I don't know, updated for the times. And it's like, put a whole chicken inside and don't wait 4 hours. It's done in 20 minutes. And you're just like, oh, that's kind of nice, right? And it's like rice takes, like, no time at all. You put anything in there, it comes out kind of tasty and just done in no time flat, all right? The reason for that is the exact same effect. What we're doing around the fluid and the food and whatever else is in there is we're saying we have a higher external pressure, which means you can have a higher boiling temperature, which means you can cook everything in there at a higher temperature without actually boiling away the fluid that you're using to cook. So you have faster cook times. So get an Instapot, I guess. I don't get a commission. I should have like an Amazon affiliate link or something. I'd make, 6 cents. It'd be fantastic. So boiling extra information with a little bit of practical advice, perhaps. All right, which brings us to the last thing here, which is a discussion of a couple of different things: partial pressure and humidity, specifically relative humidity as it relates to water and water vapor. So first of all, definition of partial pressure. This is, we'll say, the pressure gas would exert if it alone was present. So you could have a mixture of gases, but this is the pressure that just that one gas in the mixture would exert. So if you needed the total pressure of a gas, you'd have to add the partial pressures to find out what all the pressure is. So let's talk specifically about water. For water, we can say that the partial pressure has a broad range. We can say it can range from 0 all the way up to its vapor pressure at a particular temperature. For water, the partial pressure could go from 0 up to the vapor pressure at a particular temperature, which allows us to find a few things. First of all, let's see. I need a little more space. So let's get rid of some of these lines. And then I'm going to do this just for fun. And then we're going to continue this discussion up the right side. Fantastic, right? So let's see. We can define relative humidity based on this. If you watch the weather, you often see this thrown about as a number that's important. It is the partial pressure of water divided by the vapor pressure of water. And we should add in there, wow, I'm really out of space. This is terrible slide management. My apologies. Times 100% to get a percentage. The partial pressure of water divided by the vapor pressure of water. If you look at what we've defined these terms to be, if they are equal, then the air is fully saturated. It can hold as much water as it can at that particular temperature. So those are going to be, that'll give you a 1, which is 100% relative humidity. So sometimes what happens is you can get over 100% if the temperature falls suddenly. All of a sudden, the water or the vapor is holding more water vapor than it could normally. And in that particular case where you have a situation of supersaturation, and that liquid has to come out of the vapor phase. It has to come back out, which means it'll come back out and condense in the form of something like dew or fog or maybe rain, depending on a variety of factors. So relative humidity at 100%. If it goes over 100%, which can happen if the temperature drops, some of that fluid recondenses back out of the vapor form, and you end up with some sort of condensation. And then finally, one other thing, you might see sometimes the dew point. This is the temperature when these two things are equal, when the partial pressure equals the vapor pressure. So when you have 100% relative humidity. Dew point is the temperature when the partial pressure equals the vapor pressure. That is really all I want to say about that stuff. Just some terminology, some ideas, again, based on the idea that we have kinetic theory, or a bunch of molecules that are randomly moving around, causing all of this to happen. So let's jump over to the slides for 18b and talk about 3 different things to round out chapter 18, and then we'll all be legitimately excited that we finished another chapter, right? Yeah, exactly. See, now I don't know if you're lying or not. So I feel like you should be legitimately happy about finishing a chapter, but who knows? Who cares? You can just pretend to be excited. Why not? So, first of all, van der Waals equation of state. We've done a lot of work with ideal gases, and we saw that, in certain situations, ideal gases aren't so ideal anymore, so we might call them real gases, which they have properties that deviate from what is predicted by the ideal gas law. So there are some other equations that help us better understand the actual behavior of gases under all possible conditions. So we're going to build over the next 2 slides to this idea of van der Waals equation of state. And what's going to happen is we're going to go back to those 4 assumptions we had on the first slide and re-add in a couple of things that are happening in the gas with all of these molecules interacting with each other that we completely did not account for before. And that led us to the ideal gas law. So the first one of these is the idea that, well, these molecules actually have a size. So we could say the finite size of molecules. They take up space. As you get a higher and higher density, which remember that's one of the cases where we start to have trouble with the ideal gas law, well, they're taking up potentially a significant amount of space in the volume that they're occupying. Okay, so they're not just point particles. So because they take up space, this changes things. Let's see. What did I want to add to this? Their volume takes up space. So we're going to say that this is true. We're going to define the unavailable volume per mole as a certain value B, which is going to be based on whatever gas that we're using. Hold on to that constant. We'll talk about it more after we get to the end of the next slide. The unavailable volume, whatever that may happen to be, we have really no idea what it is. We're just going to give it a value per mole, which means that we could say that the total unavailable volume is equal to the number of moles times however much volume is taken up per mole. Again, by unavailable volume, we're talking about space inside the container that's taken up by the molecules themselves, which decreases the volume in which the molecules can move around. Okay? I think it makes sense that we have some sort of term for that, right? It's like it's completely unrealistic to think that molecules take up 0 volume at all. And as I get more and more of them in there, higher densities, well, it's taking up perhaps a lot of the volume in which they can move around. So what we need to do is this. We need to start with the ideal gas law and make a little change. That volume is not the volume that's available. What I need to do is subtract from that volume to get maybe a term that more properly expresses how much space is available for the molecules to move around. So we're going to change it, and we're going to say that this V is going to become the volume minus this thing NB, the unavailable volume, and leave the rest of this like we had it. So now we're subtracting from the volume the amount of volume that's taken up by the molecules themselves. And then I'm going to divide this thing through by N. Dividing through by N just to get it in the form that's commonly used, which would give us P times V over N minus B equals RT. This is known as, the Clausius equation of state. In which case we've taken into account one additional thing that helps us get a little closer to real gas behavior. The Clausius equation of state. And if you just look at that equation, I think it makes sense. If I have less available volume, right, we're taking this term, need my pointer, right? Instead of just V from before, we're essentially dropping this V, which means to keep things proportional, P has to go up to account for that drop in volume. So less available volume gives me higher pressure. Think about that for just a minute. Am I going to have more pressure or more impacts with the walls of the container if all of a sudden there's less space for them to move around? That seems pretty logical, okay? Higher pressure than expected by the ideal gas law because we've reduced the volume by some amount, okay? That's the first step. We're including the finite size of molecules. Anybody have any complaints or comments or anything about that? Or just cheers? Yeah, it's great, right? I need to drink more coffee before this class. Although, I did just finish a cup, so there's a chance that like 15 minutes into lecture, all of a sudden you're going to be like, well, he just changed a little bit. What in the world got into him? That's when the fun happens. I should just drink throughout class. Just more and more coffee until I just completely like explode at the end of class, and then I can rest. It'll be fine. There's murmuring. I'm not sure what the murmuring is about. Maybe it's because I said drink, and you're thinking alcohol. That'd be a very different class. I don't think I'm going to do that. All right, so number 2, let's consider one other thing that we left out before, and that is the fact that, well, there's going to be forces between the molecules themselves. Before, the only things that we allowed to happen was the molecules will sometimes hit the walls, elastic collisions, and sometimes they'll just hit each other basically instantaneously and bounce off. We didn't account for the fact that when they're somewhat nearby, there's going to be additional, I guess we could say electrostatic forces. There's going to be attractive forces between them, okay? So we need to take that into account as well. We're going to make a couple of assumptions about this. We are going to assume that it's relatively short range. So we're not going to, say, allow a molecule from one side of the container to be attracting one all the way on the other side. That seems a little bit ridiculous. Plus, it would be a whole lot harder to account for that, all right? Relatively short-range forces. And based on this, we're going to say that they only affect nearest neighbors. Molecules right nearby. So think about what this would do to the forces on the walls of the container, which we translated over into pressure. You could imagine that if you have molecules that are moving toward a collision with the wall of the container, so molecules moving toward a wall, feel a force from behind. Because there's going to be other molecules behind them. You can imagine I have a molecule, it's like, yay, I'm going to hit the door, I'm going to hit the door, I'm going to hit the door. Well, we assumed before is like there was really nothing holding it back. Now we're assuming there's probably a molecule that's pretty close nearby that's exerting an attractive force and essentially slowing it down just a little bit, okay? Which means the force it exerts on the wall is going to be a little less than expected. And if I sum that up over everything, that means the pressure on the walls of the container is going to be a little bit less than expected, okay? So we could say that molecules moving toward a wall feel a force from behind. This decreases the force and therefore the pressure. So let's see. We can say that the amount of reduced pressure should be proportional to a couple of different things. It should be proportional to, we'll say, the density of molecules next to the wall, because it's about like how many are about to hit the wall, first of all, and the density of the layer behind them. How much the pressure gets reduced should be proportional to the density of those that are about to strike the wall, that layer right up against the wall, as well as those that are behind them that are exerting that attractive force backwards. Okay? So we're going to define density. We'll say that we're going to let density be equal to the number of moles per volume. And from this, since I'm dealing with two different densities, those densities of those two layers, we're going to use the same equation for both. So we could say that the pressure reduction is proportional to N over V squared. I need two of those terms, or one term need multiplied by each other, because I'm dealing with two layers. Oops, I'm moving things around in my notes. Go back. Where was that? It's not good. Here in a second, I'm going to say things that make no sense because my equations moved around. Oh, no. Well, I don't know where it was. We'll figure it out. It'll be fine. All right, so this is going to be our pressure reduction. So a proportionality constant needs to be defined. So let's say that the pressure reduction equals a new constant. We used B last time. Why are these not in the other order? I don't know. I'm just following convention here. Maybe this one was done first. We're going to say that it's equal to a new proportionality constant, times N over V squared. Again, that's the amount of pressure reduction. It's how much we're going to subtract from the pressure. So, I'm trying to figure out, it looks like I flipped it upside down and then around this way. Oh, those look like equations I've seen before. That's much better. And then I made it too big. So again, starting with the ideal gas law. Actually, we're going to start with what we had before. We already said pressure times V over N minus B is equal to R times T. So we're going to already include number one, the first modification that we made to the ideal gas law. And I'm going to start by solving that for pressure so I can subtract something out of the pressure. So let's say that pressure is equal to RT over V over N minus B. And then we're going to use our pressure reduction and subtract A times N over V squared. So now we're just including number two, the forces between molecules, and our assumption of how much we think the pressure is going to drop by subtracting that out. Let's see, a little bit of algebra to get this into the form that we normally see this written. I will let you do the couple of algebra steps that are required and just say that we can rewrite this as P plus A over V over N squared times V over N minus B equals RT. And again, there's nothing really there except readjusting a couple of things. Essentially, so we get our PV term back on the left together like we have with the ideal gas law. This is what's known as van der Waals equation of state. And it's adding a couple of more realistic assumptions to help us better model the behavior in both the pressure and the volume of real gases. So notice there are two constants that live inside there. These are constants that have to be experimentally determined, okay? Dependent on the gas and whatever its particular conditions are, you can actually make measurements and determine for a particular gas, A and B have certain constants, and you can fit the equation to match the behavior of the gas. Just keep in mind, the things that we just did, right, we made sort of rough, educated guesses of the amount of corrections that were necessary, okay? They seem to make sense according to kinetic theory. We can get this equation to fit the behavior of real gases, but again, it's not really including every possible thing that's happening in the gas perfectly, which means it's just a model. It's not perfect, just like the ideal gas law isn't perfect. None of this is perfect, but it helps us mathematically model the behavior of real gases. Let me point out one additional thing. I like this last term here. Notice, the van der Waals equation is essentially just a more advanced version of the ideal gas law. This will reduce to the ideal gas law if the density is low, in which the ideal gas law actually works. What I mean by that is that, first of all, the term A over V over N squared is going to be much, 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 much less than the pressure. And also, B is going to be much, 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 much less than V over N. So if those are really small, that means this whole part of the equation goes away, the B goes away, and then I just have P times V, and we can multiply the N up the other side equals nRT. Okay? And if you're thinking, why are those two terms really small? Go back and look at where we first put in A and B and think about low density, and you can quickly see, like, oh, those numbers would have to be small at that low density. And then it simplifies back to the ideal gas law. Okay? Any questions about those two things that we did? We've got two quick things to do left in this chapter. Let me start over here.
So, like, when you're talking about the kinetic theory, you said, like, the extended all as a box, right? So, like, don't the molecules also get attracted?
That would be something perhaps we could add in there to make it even fit better. It seems like there's always a little bit more you can think about, but it's just adding more complexity, and maybe you don't really gain a whole lot if you can already fit it to some graph. I saw somebody back here. Why it multiplies pressure? The compensation one is, it's better to think of it as being subtracted from volume, and then that volume is being multiplied by the pressure. It's not actually multiplying the pressure itself. Yes, one more. That's a good point. Yeah. Maybe correction number 3. Yeah, I can't argue with that. But again, that's just another detail that you could use to try to model the gas a little bit better. Anybody else? I thought I saw someone here. Maybe your question. Any particular reason why it's a square? Then why what's a square? The density squared, it's coming from this idea that we're saying it's proportional to two different densities. So if we were only worried about the density of one layer, we would just let it be proportional to N over V. The fact that it's proportional to both is kind of like in the gravitational force, it's dependent both on the mass 1 and mass 2, and you multiply the two together to get the proportionality. Okay. Anyone else? That's the end of that slide. Yay? Ha ha ha! We finished another slide. Two things I want to talk about here really quickly. Again, keeping to the idea of kinetic theory is the idea of mean free path. We know that these molecules are sort of moving around randomly and they're going to run into each other. The mean free path is a calculation of what the average distance is that they travel before they encounter another collision. So you end up with a situation that's kind of like there on the left, where you get this meandering path as a certain molecule hits other molecules and sort of bounces around. Based on the density of those molecules, of course, the distance that it can travel without hitting something else is going to vary a little bit. So I'm not going to add too much to this. I just want you familiar with this concept. First of all, we could say that this thing should be shorter. Should be a shorter distance with higher density, as well as larger molecules. And there's a really short derivation in the book. I looked at it. I didn't think it was terribly instructive for what we want to do in here, unlike I thought there was some use to what we looked at with those two assumptions on the previous slides. So I'm just going to tell you what the equation looks like, and you can see that it agrees with exactly what we think it should be. The mean free path is given by L sub m, and it's equal to 1 over a bunch of stuff. 4 pi times the square root of 2 times r squared times n over v. N over v would be a description of density. R is the radius of the molecules. So you can see they're both in the denominator, they're inversely proportional. If either of those gets higher, the density or the size of the molecules, as expected according to kinetic theory, we end up with less distance traveled between collisions. Okay? One last point there at the bottom. Notice it says it's meaningless at low densities. If you do calculations here at really low densities, you get very big numbers for the mean free path, in which cases the mean free path might be bigger than the size of the thing that's containing the gas, which just means that it's going to hit the walls more frequently than it's actually going to encounter other molecules, okay? So if the density is low enough, it's more the walls that are restricting, that are causing interactions as opposed to collisions with molecules around them, all right? And then finally, diffusion. Diffusion. I kind of like the way diffusion is explained here because it's one of those ridiculously logical things that almost seems too simple to explain anything. Diffusion is simply a mixing of fluids, whether it's a gas or a liquid, due to the random motion of molecules. And you can see it illustrated up there where they're taking just a little bit of, I don't know, I guess it's food coloring or something, and putting it into some water, and it all starts highly concentrated in one area. And if you just wait, don't do anything, you don't have to shake the glass, after some period of time, it seems to disperse itself completely through the other liquid. Well, this is happening not because of some external force, but just because of kinetic theory. You've got all of this random motion of molecules that are essentially serving to stir the liquid on a molecular level, okay? So this always happens where it will occur, or the fluid will diffuse from a region of higher concentration to lower. It would be really odd if it went the other way around. Like you spread it all out and then it just goes and clumps itself back together. That would be a different effect altogether. Question? That would be reversing entropy. Yeah, that would be odd all the way around. Entropy we'll talk about in a couple of chapters. Good. And this is dependent on concentration, which we could describe as molecules per volume. And notice this little diagram on the left. They're simply looking at a cylindrical container that contains one fluid, and then we're going to put some other fluid represented by the little orange bubbles or whatever there into mostly the left side of the container. And then we wait a couple of minutes and maybe get into this state where it's like most of them are on the left-hand side, some of them are in the middle, and a few are hanging out on the right. Like imagine we've made it to this far, but still all of these little orange dots are moving around randomly, okay? So that means every little period of time you're going to have some of the orange ones that happen to leave this far left side of the container and enter this middle region. But even from over here, because there are some molecules on the right-hand side, you're going to have some of these that occasionally find their way into this middle region. Okay, that seems to make sense. The thing is, you're going to get more entering this region from the left-hand side simply because there are more of the molecules over there. Based on random motion and a higher concentration here, more are going to enter from this side than enter from the other side where there's a lower density of those molecules. Based on that, you're going to continue to get diffusion of molecules from the higher concentration to the low, until there are essentially equal concentrations on those two sides, and then you're going to have equal numbers that are coming into the middle region from both sides because of the equal concentrations. I think that's about all there is to say about that other than give you some equations. So, let's see. There is something known as J, which is the rate of diffusion. And it is equal to D times A times C1 minus C2 over delta X. And I need to define what a few of those variables are. This D is a diffusion constant. And it will be dependent on both fluids. And you can find a table in the book for mixing of a few different items. Diffusion constant is depending on what you're putting into the fluid and what the other fluid is. A there is simply the cross-sectional area of the space through which things are diffusing. And this whole last term could be written as the diffusion gradient, where C1 and C2 are concentrations. You could also write this in a differential form if you wanted to. I'll trust you can find that in the book if you'd like. The only other thing that I'll tell you is this is known as either the diffusion equation or Fick's law, F-I-C-K. And I think that is all that I wanted to say. Chapter 18 is complete. A few of you are awake, but honestly, you didn't sound excited enough. This is what I heard. Chapter 18 is complete. Like overall, there was some noise that was made, but if I isolated individual people, you weren't terribly excited. And that's depressing, you know? I mean, we finished a whole chapter. Like 17 and 18 are now done. I know, that's fantastic, right? I give up. What's that?
We're closer to 21.
We are closer to 21, right? What we want to finish is 17, 18, 19, and 20. Because remember, those are the chapters I don't like as much. And then we get to 21. Life will be fun at that point, all right? Or not, depending on whether you like this stuff better. Who knows, all right?